Okay, so let's continue with our exploration of the equilibrium constant, also known as the mass action expression. Please turn to equilibrium KEQ, the nature of equilibrium. This is a review of what we did on Friday. So a reaction in which the products can recombine under suitable conditions to produce reactants is called a reversible reaction. When the rate of the forward reaction and the rate of a reverse reaction are equal, a state of chemical equilibrium exists. The mass action expression, don't let this confuse you, it's a snapshot in time. It's the same mathematical setup as the equilibrium constant, except your system isn't in equilibrium yet. So basically it's products over reactants where coefficients become exponents. We talked about this. They give the mass action expression the letter Q. It's the same math as KEQ, it's just, well, is your system at equilibrium or not? You can compare a value of Q to a previously determined value of KEQ and see which way the reaction is going to go. The brackets represent concentration in moles per liter, and here are 4 problems to practice writing the mass action expression. We just used Q instead of KEQ. I'll let you guys fill that one in, but it's products over reactants. It's pretty straightforward. So the equilibrium constant is the same thing as the mass action expression for a system in equilibrium. Don't let these crazy brackets on this typo fool you here, okay? It's just products over reactants kind of deal. Notice it's the same math. Numerical values for the equilibrium constant are always positive. They show the extent to which the reaction proceeds. When the value is big, when it's bigger than 1, it favors products. When it's small, less than 1, it favors reactants. Probably going to want your notebooks, some separate paper here as we get into the next page. Okay, I'm going to do this on separate paper as we go. So, here's a blank one. Need your calculators as well. Apologize for the shuffling of papers. But it says you've got this system 2A gas plus 3B gas, double arrows, go to C, gas plus 2D. Takes place in a 10-liter container. I want you to add a dot. Make that 10 dot. We'll keep at least 2 sig figs. The amount of reactants in the original mixture and the amount of B at equilibrium are given. Okay, so those are clues. So I'm going to rewrite this. You've got 2A gas plus, hope you can see this today, 3B gas, double arrow, C gas plus 2D gas. Now, we could say Q or KEQ would be C times D squared over A squared times B to the third. Okay, we all know about that. What we're going to do is we're going to use an icebox type of setup to solve for the concentrations and then plug them in and solve it for KEQ. So the players in the game, you've got A, B, C, and D. I, C, E, and then brackets for your concentration. Now, A and B are reactants, C and D are products, so usually you put a squiggle there. We start with no products, so you're always starting with 0. You're always losing reactant and gaining products, so you're going to put a minus for your reactants and a plus for your products. They said you've got a 10-liter container. Well, this is moles per liter, so whatever this is going to be divided by 10. And they gave me some values. They said you had a container and you put in 4 moles of A and you put in 5 moles of B, and then at equilibrium they said you had 2.6 moles of E. Okay, well that's a clue. if you started with 5 and you have 2.6 currently, 5 minus 2.6, you must have lost 2.4 moles of B. Now that is the basis for the rest of your changes. All of your changes are based on stoic. So if you lost 2.4 Bs, well, the stoic between A and B, 3 Bs down here, 2 A's up there. That's going to give you a change of 1.6 in terms of A. And if you had 2.4B, 3B down here, 1C up there, that's going to give you a change of 0.80 for C. And 2.4B, 3 B's down there, 2 D's up there, that's going to give you a change of 1.6 for D. Now I can't stress that enough. It's the stoic line that's the important line. Use stoic to get your changes. From there, it's arithmetic. So you had 4.0 A's, you lost 1.6, you're down to 2.4 A's. B is filled in for you. You had no C, you gained 0.8, that's 0.80. And you had no D, you gained 1.6, that's 1.6. These are how many moles you have left. Divide them by your 10 liters. So 2.4 over 10 here, 2.6 over 10 there, 0.80 over 10 there, and 1.6 over 10 there. This is 0.24. This is 0.26. This is 0.080. And this is 0.16. These are the values that you plug into your mass action expression and solve it for KEQ. So you'd say KEQ is C times D squared over A squared and B cubed, which is going to be equal to 0.080, which was C, and then it's 0.16, and that's squared, over 0.24, and that's squared, and that's also over 0.26, and that's cubed. So if you're using one of these calculators or something similar, I think you'll find this caret key to be useful. I'll see if I can plug this in where you can see it. Alright, so top times bottom divide, we've got 0.08. Oh, you don't need the 0, but that's fine. Can you see that? Times 0.16. Raise that caret button here. Second power. Hit enter. Divided by, we want 0.24 squared, so 0.24 caret second power, enter. Also divided by 0.26 caret to the third power, enter. And that's 2.0229, yada yada yada. We're going to keep 2 sigs. It's roughly 2.0. Alright, so you're going to do the next one, number 8. It's pretty similar. Next part of our lesson here. Let's see how far we're going to get with this. So we had just done the homework 1 through 6 here. You will find number 7 is one of those problems. And numbers 8 and 9 are as well. We'll talk more about the next pages after that. So, your homework today then. You are going to do the worksheet we were just on. You're going to do numbers 8, 9, and 10. And then you're going to backtrack to the equilibrium page that we had our previous homework on. And you're going to do numbers 7, 8, and 9. Okay, I'll summarize that on the page. I'll put it in the instructions on the Google Classroom. All right? Happy Dingus Day.